Yeah, I'm Everett Hildenbrandt. I'm at Runtime Verification. We've been doing commercial formal verification for a while in different domains, and we're getting into Rust. And so I want to talk to you today about K-MIR, which is the K semantics of MIR, which you can, I think most people here know what MIR is. So, yeah. So, I mean, most of us are pretty motivated to do formal verification of Rust, but I'm going to motivate you a little bit more about that. And then we're going to talk a bit about how our tool works, and it's a pretty similar pipeline, I think, to Connie, actually. And then I have a bunch more slides and some demos and some things. I don't even know if this overview is up to date, so we'll just keep on going. Yeah, this is why formal verification matters for people who aren't familiar with that, but there's a whole spectrum of quality assurance methods. Formal verification is the highest end of that spectrum. And in safety critical systems, that's what you want to use, especially if the lines of code is small. So we do a lot of work in the blockchain like Web3 space. There the amount of lines of code is really small, but the safety criticalness of it is really high, and so we're paid to do formal verification in that space. Yeah, and as we've seen today, Rust has a lot of great safety features. I'm not really a Rust expert, but there's limitations, and people are trying to get around these safety features. And beyond that, you just also want to start to do formal specification of the correctness of code and the correctness of systems. So that's beyond even just the what you're getting with the type checking and the borrow checking. So so that's why we want formal verification tools for Rust. So K-MIR, we pretty much use symbolic execution for all of our formal verification approaches. Our approach is based on having an operational semantics of the programming language that we are targeting. So in this case, that's MIR. And that means we're not doing what I would call like static symbolic execution, where you're building like an SMT formula and then throwing that to a SMT solver. We do something that I would call a little more like dynamic symbolic execution, or explicit state symbolic execution, where you're representing every state explicitly and making transitions in a transition system between them. And this has drawbacks and it has benefits, so I'll talk a little bit about that. So just to give a quick little demo of K-MIR, the tool itself, or a couple of the tools here, I'm just going to run like a proof viewer here. So over here I'm calling bash demo. This is what demo is. It's prefixing these things with the CUV run thing, which don't worry about that, but this is the command. K-MIR view proof dir proofs, and then it's this CMP proof, which just is a really simple Rust program. It's just main and a bunch of asserts that various comparisons are, comparing things correctly. And we have them in different functions to force the compiler to not inline them and make them trivial and make it do nothing basically. But I just want to show you a little bit about what, this is the interface that we're going to give someone who's very motivated to do formal verification of their programs. And so I just want to kind of give you a feel of what this looks like. So over here on the left is a control flow graph where the nodes are representing different states. And so here you can see we're in node 1, and that's kind of like our initial node. And you can see we're going to be calling the CMP symbol. Well, no, that's actually not true. We're actually initializing the program at all, right? And then we'll be stepping into the CMP thing. We're in function main right here. Down later, we are stepping into executing the program. There's updates to different parts of the state here, like this is the current body that we're executing. The caller was main, which we represent as type -1. We have the locals here, so you can see all the state that you'd assume is present when executing a MIR program, basically. And then there's a bunch of different steps, and here's a transition of 50 steps right here that goes from this state to this state, for example. And if we look here, you see there's this rewrite arrow that shows us kind of like this state delta between those two states. And so we actually are building not only each individual state, but these deltas between the states, and we can kind of reason with that whole data structure there. All of this data is represented in K's language called cast, and it's being kind of pretty printed or ugly printed here for you. So I just wanted to kind of show that that's what the results of symbolic execution look like. This was a proof I ran earlier today. I can rerun it again up here, and you can just get an idea of what the, proof output looks like. We're initializing the prover, starting what we have, which is called a core server. That core server is being used to, answer symbolic requests. So we have like this Python library called pick, that's what you see here, which is talking to a server that can do symbolic reasoning, and that's the Haskell code base that does that symbolic reasoning. And it does, a bunch of symbolic reasoning all through the execution. This is a concrete test. There's no symbolic inputs, and so it just executes straight through it. And it goes, to depth 693, sort of 693 states between there. And then it gets to the end, and at the end of execution, it checks that the final state that you have is subsumed into what's considered to be like a successful state, which in this case, we're just saying reach the end of execution of the program. That's all we're saying about that final state. And that's enough for if all you're checking is, are your assertions, are your violated assertions reachable? Did you run into unsafe behavior? Did you, because that, in those cases, we halt. That's how we approach this. And then it gives you a little summary of what the proof status is. And a real world proof, like what we do for Solidity smart contracts, the numbers of nodes here are going to be like in the hundreds to thousands of different types of nodes in the graph, and there's branches, and it's a lot more complex structure that you're working with. So you'd be jumping around and you'd be inspecting the branch conditions on the branches and stuff like that. So I just kind of wanted to give you an idea of what using the tool would look like. Yeah. So that's K-level semantic steps. So K is an operational semantics framework that lets you define kind of like a state, basically, and then define transitions between those states. And we give operational semantics to programming languages by writing down such a transition system of how to evaluate the program. And every transition between states is one step, basically. And so in the case of MIR, I'll show some example rules later, but in the case of MIR, an example rule would be, I'm about to evaluate a binary operator. Okay, pull out the arguments, evaluate the arguments, and then that triggers more steps, and then those are kind of cooled back in, and they're placed in, then the actual operator's called, and stuff like that. So kind of every little logical step of execution kind of is one step. In the case of something like EVM, which is the Ethereum virtual machine, one opcode is actually broken into like 10K steps. And so even just executing a single opcode takes like 10K steps. Even just executing a small fragment of an EVM bytecode takes like 1,000K steps just to get any progress. So that's one of the things I want to talk about today is the reason we're targeting a language like MIR instead of a lower level language like EVM or WebAssembly, like a code gen language, is just sheer number of smaller steps, basically. Like you can just get further into the execution faster. Mm-hmm. That it reaches the end, yeah. Yeah, so, yeah. So I'll break it. I just said, compare less than or equal of 4 and 4 should fail, and it will succeed, right? And so I will run the proof again, and it should, come back failed. Yeah. So proof status failed, and then so this proof log that we're getting, I usually have it turned on. Normally it would be turned off, and this would all just be empty. But here we can see the execute request came back, and it stopped 219 steps in instead, and it was like, oh, I hit a stuck node. And what happens is it hits that assert that I changed, and it can't make progress, right? Like the assertion fails, the execution stopped, basically. And so what we're trying to prove about the program is execution reaches the end of the program in a successful state, right? Like the whole program gets executed, and because that doesn't happen, the proof fails. So I can show you, I'll show a little bit later what that means in a little more detail. Okay, so I just wanted to give a flavor of what this tool looks like. And then I'm going to talk a little bit about why we take the approaches we take, even though it looks so painful. Yeah, well, this is, we're Runtime Verification. We do software quality assurance. We've done a lot of stuff with blockchain things. We have many different programming language semantics we work with. And it's all open source, so that's pretty cool. This is the high-level slide of how the heck does this whole thing work. And this is going to be a pretty familiar diagram to everyone in this room because a lot of the people here have had, similar diagrams they've pulled up. But yeah, we start with a driver that grabs onto the Rust C, analysis plugin framework thing. That's the limit of my understanding. It grabs the source code as well, that gets compiled, and MIR is emitted. So we wrote this thing called Stable MIR JSON, which plugs in and basically uses the Stable MIR plus MIR interfaces because it's not quite fully fleshed out that you can only use the Stable MIR yet. Extracts a bunch of JSON information about this is the MIR of the program and some other metadata that's useful for us, like source maps and things like that, and dumps that into a JSON file. So kind of skipping ahead here, but and I think the extraction point now, we do monomorphization now instead of we do a little bit of monomorphization. It was unclear to me what the thing was. That was an interesting thing from earlier.
We monomorphize, but we're running into problems where sometimes we're finding that unmonomorphized stuff can leak in unexpected places and it's hard to notice.
Yeah. Yeah, so but we're trying to, as much as possible, just follow the same pipeline that the actual compiler follows, using the same data structures that the actual compiler is using. My opinion is that's the only way to really scale to industrial grade verification, where you're using the exact same tool chain that your users are expecting. So we got some changes merged into Rust C to introduce like Serde serializations of some MIR and stable MIR data structures. That's all, we're going to try to get as much of this as we can just in Rust C itself, because that way we don't have to maintain it. But we'll see. So more stuff here, and then eventually what happens is that JSON stable MIR, our tool consumes that as an artifact and builds our version of that AST of the MIR, basically. And then we're able to do symbolic execution in that transition system of our version of that AST, which again is called that cast format. We actually have two formats, cast and core. Cast is kind of like a higher level, and you can elide the sorts of variables and stuff. Core has to be fully detailed about all the sorts, and it's using sort injections instead of subsorts, for example. And given the K architecture, we also get like a concrete engine and a fuzzer and stuff like that. So, and all of this is made accessible via like a Python library that gets you access to all of the K's functionality. So you get access to the fuzzer, the concrete execution engine, the symbolic execution, the prover, stuff like that. So, yeah, already kind of talked about MIR. I mean, the reasons to target MIR, I think many people here probably already know, but I'll say our reasons at least. Borrow checking's been done, type checking's been done. You still have the original control flow of the program somewhat intact, so it's easier to map error states back to the original program. That's super helpful for debugging. We found in other systems, like in Solidity, for example, when we're doing symbolic execution at the EVM bytecode level, mapping back to the Solidity code is an absolute nightmare. And so having that higher level of representation is a huge win. When we started out on this, we saw this Stable MIR project, which I think the Connie team is pretty familiar with, or had people on it that were familiar with. And we decided to target the Stable MIR thing, the idea being that we wouldn't have to be as brittle to compiler changes. I actually don't quite know what the status of all that is, but I think that's still kind of the goal. And we have found some issues where Stable MIR is not quite exposing the information we need, so we have to reach into the MIR API directly and pull out that information and include it in our own serialized Stable MIR JSON. But maybe just having this common JSON format with a schema and everything is something that can help that effort all converge a little bit more. And maybe that's even something that like Charon can consume as input, that Stable MIR output. Because Stable MIR JSON's not our dream, right? So it's what we needed. Okay, so we do have this Stable MIR JSON tool. It produces actually kind of nice, like, I don't know if you can, yeah. This is textual MIR, and then it produces like these JSON files over here. But another thing that it does is it makes these like dot graphs of the whole entire, graph. There's already a tool that does this for MIR, but this does it for Stable MIR, so that might be a useful tool if you need that. And in particular, there's a bunch of kind of noise here about like initializing the execution. The stuff over here is actually the code that you wrote and that you'd expect to see. So this is of some Fibonacci number sequence, and so I'll just show the commands to get that real quick. This is just part of Stable MIR JSON, which is a Rust compiler driver package we made that can pull out the MIR JSON, and it can pull it, and it can make this control flow graph the same as already exists for MIR, I'm pretty sure, but just for Stable MIR instead. And we made it a little prettier and included some more information and stuff like that. Like we got the locals printed out here, and so just to demo it working, we have, in this subdirectory is our Stable MIR JSON, which relies on using a certain fork of the Rust compiler. So I think I can, or nightly, yeah. So you have to use this nightly version of the Rust compiler, which has our features that we got merged into Rust C present in there. And then it can, you can do cargo run on this Stable MIR JSON on the particular file that you want the Stable MIR JSON output of. And then you can also throw the --dot option to get a dot file instead, basically. And then you can use a normal dot visualizer to visualize that dot. And so I'm not going to run these commands right now, but I'll show you what the output, they're instant. They run like that. But I just don't want to break anything on my system in case the demo gods are mad at me. So this is, it's a lot of information that's being output here, right? But you got like the allocs, you got the functions with their kind of mangled names, and you got the items here, which are, all the items and stuff, and you can kind of get that information out. We added just recently this thing that we call the spans, which is like the map from the span ID to the source code line and the offsets and stuff like that. That's so that we could do some debugging output when we're doing the symbolic execution. So there's, it's pretty easy to just add more information into this output format. It'd be nice to kind of converge on something that's useful for everyone. So that's the Stable MIR JSON. Any questions about that? Yeah. Yeah. Yeah, so it's kind of in progress. So my understanding is it's more stable than the MIR. It's still not quite as stable as we'd like, but it, it has goals and ambitions.
So the motivation is what you mentioned, like in the past, we used to do frequent tool chain upgrades, and our code base would break like every few days. So this was the main motivation for coding the Stable MIR API.
And that, yeah, it sounds like it has a lot of overlapping goals with Charon as well, which I wasn't aware of that. So it's a good thing we're doing this. So we're all kind of getting aware of all the things we're doing. So the semantics of Stable MIR. So I'm going to jump into like what the heck is a K semantics at this point, right? And so K framework it's an open source framework for defining operational semantics. It started as a tool for teaching programming language theory to undergraduates, basically. And that was quite a while ago. And it was mostly just to make it very easy to build kind of real-ish toy programming languages very quickly. Later, it came with a symbolic execution engine as another kind of grad student project to attach to that semantics framework. And then later it came with also a logic formalizing how it actually does transitions and is able to make kind of proof objects basically, and that's the matching logic thing. But I mean, I give you that history just to give you an idea. K is an engineering effort, right? Like the idea of like programming language semantics has been around for a while, right? it wasn't like trying to break theoretical ground. It was engineered to scale to large programming languages. And so some of the first languages that it targeted were C and Java, for example. So we have a complete semantics of the C17 ISO standard, including undefined behavior, passes like the Julia test suite, conforms with GCC and Clang on all defined inputs. So that the goal is to scale to actual programming languages with this framework, not to make toy models or something like that. And then the other goal is to represent them directly, right? Like not to do something where you translate the language to some intermediate representation and then reason over that intermediate representation, then effectively your translation module becomes part of your definition of the semantics of the language. We want to reason directly about executing things in that language itself. That, of course, gives you really good debuggability and inspectability into intermediate states when you take that approach. So classic problem is, there's too many tools. You have an interpreter for C and a symbolic execution for C, but the same for Solidity or something like that. And K is trying to solve that problem. We have one interpreter we have one LLVM code gen that we derive from K definitions. We have, one model checker, one verifier, one, prover, one parser, one debugger, and that same tool then gets instantiated to all the languages we have semantics for, right? So it's kind of like an economy of effort type of thing. So what the heck does these K rules look like? Well, it's actually really simple, right? Like you can think of it as like you're living in the state non-determinism monad, right? And if you're living in the state non-determinism monad, you have to define what a state looks like, right? And we do that with something called a configuration. And then you have to define what transitions look like in your state non-determinism monad. And so we define this thing called a configuration that gives us our representation of state, and then we have rewrite rules which transition between different states, and then you can supply what are called functional or equational rules, which take a state, which is a term in a term algebra, and simplify it to some normal form, basically. So I'm just going to kind of go through a few examples of what that looks like, just to give you an idea. This is, can you see this, guys? Okay, yeah. So my eyes bleed when I look at these things. They're not meant to be looked at that much, but there's a lot of sharp, pointy things. But this is a MIR state, right? So here's your current frame with your current locals and some other data that has to be kept around for your current frame. Then there's a stack of frames, right? There's a map of functions. There's a memory map, right? There's a big fix me right here. Unclear how to model. There's a types map and ADT to tie map as well. So just different things you need to be able to actually execute programs here. So then what we're going to do is we're going to, there's a bunch of data structures defined in here, like this dot list thing. That's a data structure, right? And the no basic block. These are all data structures in appropriate types. But this is an example of like a transition rule. So we're about to execute a terminator of function calls. So we're about to step into executing a given function call. Well, we have to set up the callee data, right? That's what this guy is doing right here. And then there's a bunch of stuff that gets updated in the state. So the old caller gets replaced with the caller, the old destination gets replaced with the new destination, blah, 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 blah. And the stack gets a new, our stack frame gets a new stack item pushed onto it with all those old values, which are going to be popped back off at the end. So we're just kind of saving that state, and we're going to restore it later and stuff like that. So it's not super surprising, probably. I know they're hard to read, but it's like everything you'd kind of expect when defining the operational semantics of a programming language. And so you just have to be really explicit and define everything. And then we have tools that actually will render this as LaTeX, where now the cells become new commands in LaTeX, and you can, give them whatever definition you want to give, a particular flavor of visual satisfaction to yourself. I don't even know what that sentence means. All right, here we are. So this is like evaluating an R-value aggregate, right? And this is an example we were talking about earlier. Okay, to evaluate an aggregate, you first got to evaluate its arguments. You got to go and read potential values they might be referencing, put them together, do some computation on them, then pack it back up into the aggregate again, for example. And once it's packed back into the aggregate, now it gets this wrapper, this typed value. That's an actual value that's ready to be stored somewhere or something like that. So you can see that kind of like the idea of typing semantics leaks into this operational semantics a bit. And but hopefully not too much. So yeah, I just wanted to maybe do another couple little examples of these rules. I think I had something or another here interesting, but maybe I didn't. Yeah, probably not. I don't know, this was like binary operators and other things. You know, a lot of operators come down to, like, here's an example of some functional definitions, right? CMP op bool, right? Takes the binary operator and the two binary operators and basically lifts the K variant of these operators into, you know, what's needed for the Rust variant of these operators. And sometimes, you know, you have to do a little massaging, or you have to be wrapping it, doing modular arithmetic or whatever, and that's when you make these kind of wrapper functions for doing that. All this to say, oh, here's the Stable MIR JSON repo. All this to say, like, and I'll talk about this a little bit later, you know, we need to be explicit, we need to be precise, we need to be modeling exactly what's happening with the mirror in this case, but ideally, users aren't reading this stuff. They're not seeing these K configurations. And so what I'm showing you here is kind of like an expert mode of the verification tool. Ideally, you're sitting in your Rust file and you're seeing error messages that are relevant to your Rust file. So we'll talk about that a bit later too. Okay, so yeah, so we have this, you know, once you have this MIR file here, which, like, I have this Fibonacci MIR, but I have another MIR file earlier, which I'm gonna use that one because I have less anxiety about it not working. So one thing we can do, given a MIR file here, so let me do that. So we have that CMP program, which is just doing all those little comparisons and stuff I showed you, right? Well, we need to get that and turn it into a K specification, right? Some sort of K claim. And that's, GenSpec is one approach to doing that, right? And so I'm gonna call that bash demo, and it's gonna give me an error, I guess. What? There we go, that seemed to work. And it generated, CMP, there we go. It generated this file, which is a K claim, okay? And so this K claim looks kind of like those K rules I was showing you, those semantic rules, but now they're interpreted as proof obligations instead of as axioms, basically. And so the way to read this is, if I start on the left-hand side, is it the case that on all finite paths of execution, I will eventually reach a state that is characterized by the right-hand side of this rule, right? Where, you know, for example, in the ret val cell, the right-hand side, we're not asserting, it's just a new variable called ret val cell. So we're not asserting anything about the final state of the ret val cell, for example. And the same with the current function cell. But in the K cell, we're specifically saying everything that was present on the K cell, which is kind of like the current computation, has to go away. It has to be the end of the program. And so all we're proving with this specification we've generated is execution reaches the end of the program, basically, right? This prover that we have, the default one we kind of exposed via this interface, is a reachability prover, which is weak exists finally for those who like temporal logics. That means, like, on every execution path that you have, eventually you will hit a state that's characterized by the right-hand side, or it'll loop forever. It'll be it's a partial correctness type of thing. So that's one way we can generate a spec. We can run that spec directly as a proof. It'll pass. It's not, you know, it'll take a few seconds. Not super interesting to do here. Then another thing we can do is we can actually run smear JSON directly, and this is using our concrete interpreter for smear. So let me actually see if I can do this. So this is going to run the Fibonacci example, and I hope it works. Yeah, okay, so it runs it, and it, you know, you get like this huge nasty thing because all the stuff has been initialized, but we get to the sharp end program here, and most of the time is spent in setup and stuff, but once it hits our concrete interpreter, which is an LLVM code generated implementation of the transition system, it's pretty fast. And so this interpreter can be used, like, for example, we have projects where we're taking our KEVM, our EVM implementation interpreter, including it into an actual blockchain node client implementation and using it as the interpreter for that network, and it's working fine. It's slower than like a compiled language like C and a hand optimized thing, but it's still pretty quick. And there's options you can pass to this, like depth, you know, 15, and you get some intermediate state instead. So that's, again, 15K steps to take, and then it stops. Unless 15K steps took us to the end of the program. Yeah, so now we're somewhere in the middle of execution where we're about to execute a terminator kind switch int or something, right? So you're really good inspectability into the intermediate states using this approach. Okay, how am I doing on time? Good, okay. So executing K-MIR, we can do that. Configurations, we kind of talked about that. That's that state declaration that we have. MIR has a pretty small one. Other semantics we have much larger ones. Small is good, so that makes symbolic execution a lot faster. And yeah, we talked a little bit about what the property specification looks like. I showed you what a K claim looks like. That's kind of like hard mode K, right? Like you have to write out explicitly all the transitions exactly as they're supposed to be for the whole K configuration. So that's definitely hard mode. We want to do easy mode, right? So this is what I showed before. You do this gen spec thing, and it produces that specification, which is like, this is hard mode verification, right? But some claims you only can achieve with hard mode verification, right? But we'll talk a little bit about that in a second. But easy mode verification, we want it to be fully automated. We want people to be living in the Rust world, right? We don't want them to have to drop down to the MIR world even. We definitely don't want them to drop down to the K world, right? Like that's too low to go. So as much as possible, we're trying to keep them in the Rust world. So I'm going to break that promise right now, but I'll show you how we're trying to keep it at least. So here we're taking that same cmp.rs program. It's this really simple program, just does a bunch of simple assertions, and I'll fix it again. And now we're going to use, instead of the gen spec command, which generates the K spec, or the run command, which does concrete execution using the concrete interpreter, we're going to do the prove rs command, which takes a Rust file, compiles it with that Stable MIR JSON to get the JSON out, uses that JSON to populate an initial state where we're calling, the main function on a given piece of MIR, which Yoast has some work to actually make it so that it's not we're able to not just call the main function, but any function, and any function with arguments even. And so we can start it in a kind of symbolic state. And so now it's going through and it's doing the execution. It started up our symbolic reasoning server. That's what this is, that core server. And then it's going through and doing something that says, okay, proof passed, great. And so what do we do with a proof that passed like that? Well, we want to view the results of that. So I'm going to do this one. So this is, now we're doing the K-MIR view command, and I'm telling it, when I ran this prove rs command up here, I told it, hey, go save the intermediate artifacts of the proof in this proofs directory. And now I'm going to say K-MIR view, go read from that proofs directory the CMP artifact, right? So do that demo. And it brings up, okay, there's my initial state, takes 693 steps, I end up in a final state, and that final state, and you see this dash, means is subsumed into, is fully characterized by this state right here, which is just the state that says execution finished, right? We had the final program. So we'll break it, we'll take another look at it. And then I'm going to play around with some different options that we can pass to this thing, which probably won't surprise anyone. Okay, I hope this fails. It looks like it only got the 219 steps right there, so, something happened. And it is proof status failed, nice. Okay, so now we're going to view it. And now we have, okay, from the root, we get to 219 steps, and we get to a stuck leaf state, which means I wasn't able to make progress on this, and I wasn't able to show it was subsumed into this state. And here, okay, we can tell why it wasn't subsumed, because it's got this big old thing on the K cell, and the target state says just end program. So like those aren't the same. So it's not subsumed into that target state. So one natural option you might want when you're debugging a proof like this is, okay, what happened right before it failed, right? Like a few steps back. Why did it get to that state? And we have a lot of options on our more developed tools for doing that type of inspection, but the simple one we have now is max depth here. And what this is saying is, take at maximum 50 steps of execution before saving a node in the, and I'm going to do or true here to get both of these working. Take at most 50 steps of execution before, stopping, snapshotting a node, saving it in the KCFG, and then continuing execution, basically. And you'll see this takes a lot longer because it has to kind of round trip through the server. Hey, give me 50 more steps of execution, take that back, store it, give me 50 more steps, take that back, store it. So you can see it's getting basic blocks at depth 50 pretty repeatedly right here. And so remember the overall execution was 219 steps, so we're gonna have to get up to that amount. Okay, now it failed. And now we have more steps of execution here in the middle. And if you're paying attention, we have like these spans here, which are, I'll talk about that in a second. But again, we get to our intermediate state, and we're like, okay, we're still at that execute terminator. We have 19 steps here. I'm still not convinced about what's going on. Okay, another, oh shoot, I should get that node number. Another kind of debugging tool we have here is we can do what's called pruning the proof. We can, we can remove a subtree and then resume again from that subtree. So I'm going to go here and remove the subtree starting at node 7. And I did not try this before, but I always give my best demos doing things I've never tried before. Yeah, that's okay. So it pruned the node, and now if we look at the proof, and I will emphasize again, this is hard mode verification for our engineers and very ambitious people. Now it's leaf pending instead of stuck leaf, basically, right? And so if we were to resume the proof now from this point, and we were to say, okay, now I want you to do the proof again, but this time don't reload it from the start, resume from on disk, and give me, instead 4 steps of execution per basic block. So I'm gonna do that, and then I'm gonna launch the viewer on that. And I mean, we all know why this proof is broken, but shh, don't tell it. So it's because 4 is indeed less than or equal to 4, turns out. So we're doing basic blocks at depth 4 now, and we're going to view the proof.
The proof is continuing from the point where he pruned the node. It's not going from the whole side.
Right. I hope. Yeah. So now we have, that prefix where we had steps of depth 50 up until we get to that node 6, which we had pruned after, and now we have steps of depth 4, and we have the intermediate states leading up to that, basically, right? So I just want to give you an idea. That's kind of what when we're doing verification for Solidity smart contracts, this is a lot of what we're doing, right? Is going into this interface, inspecting nodes, and right now, because we don't have symbolic arguments working, which should be working probably next week, there's no branching, so I can't demo for you what branching looks like in this interface, but it creates like a branch, and you can step into either side, and you can see the path condition that led to that branch. And so you have the whole tree of execution you can explore from this interface. Again, this is hard mode. I'll talk about easy mode a little bit later. Okay, so this is active hardcore development mode, very early stages. There was a lot of kind of engineering infrastructure we had to get in place to make this possible. That's in place, or a lot of it is in place now, and we're very much like blazing forward on the semantics as far as we can. The 3 pillars that we have for K-MIR right now, we have the Stable MIR JSON tool. I want to figure out with the Caron team, with the Connie team, like where does this fit? How are we going to make it so we're not duplicating effort? We'll get that sorted out. The semantics of Stable MIR, that's the meat of our approach. We have to have that semantics. It has to be accurate. It has to be tested against actual Rust programs to make sure we're getting agreement with the Rust compiler. And then the K-MIR front end is all the nice sugar in Python for making this, lifting it closer and closer to being a Rust level verification tool, basically. So yeah, then another one, why Stable MIR JSON? Well, we want the common format, so we'll figure that out. Semantics of Stable MIR. So why this K approach at all? Why, right? Like that, and the answer really is economy of effort. But I want to see if I can convince you of that right now. And so I'm going to show you a couple of other tools that we have. Control is like this K-MIR tool, but for Solidity code compiled to EVM, basically. And you use control to do formal verification directly, on code bases how you'd expect. You're getting like the same log messages. And we're seeing commercial adoption of control. Like we use it, of course, for our engagements, right? But bringing to users a property testing interface, we use property testing as our way of getting specifications from users, in the Solidity ecosystem where code is small and motivation is high to assure that there are no bugs. Even just totally normal developers coming from the Web3 background are picking up this stuff, right? And so if you meet the developers where they are with this tooling and you really focus on staying in the language they understand, they can pick it up, right? And so that's one thing, about this approach that I like. It's worked. We've been able to get users. So maybe that's not a very good argument for YK, but another argument for YK, here is a debugger called Symbolic, also for Solidity code. It lets you go to a specific function and click a debug button, and then it will give you that execution graph. And you can step through nodes, and it'll take you to the Solidity line. It'll let you inspect intermediate symbolic variables and path conditions along the way as you're doing that execution, right? That's pretty powerful, and that's something that it takes very little effort for us to take that tool and port it to other languages, like the K-MIR semantics or the Java semantics or the Python semantics, right? So we get this economy of having built the debugger once that hooks up to K's state format, and then getting that same replicated, that same user experience replicated across different languages. So, and then another example of a tool is Comet. Comet is, so these are 3 out of probably like 8 tools that we're working on actively right now. Comet is Rust smart contracts compiled to WebAssembly. So it's using our WebAssembly semantics, which we developed back in 2020, and we've maintained since then. And here, again, users write Rust property tests, and it compiles it to WebAssembly, compiles it to both verification conditions via symbolic execution and a fuzzing harness via, we're plugging in, some high-powered fuzzers like HongFuzz or libafl and stuff like that. So again, same thing, same story, like meet the developers where they're at, Rust property tests in this case, but we need to provide the ultimate level of guarantee because it's going on the blockchain as a WebAssembly program, so we need to verify the actual WebAssembly code. That's what Comet does. And again, economy of effort, right? Like we were able to reuse almost everything from control when making Comet. Yeah, and then the keynote, I think it was yesterday, the AWS Director of Science was talking about meeting the developers all the way. I couldn't agree more. That's what, it's not, when we're talking about like making safety critical code for airplanes or something like that, the people writing the code for those or designing those systems, it's not their job to become formal verification engineers. It's our job to provide them tools that they can do their job for. So it'd be having someone learn another DSL or learning like an annotation language or something like that. That's as much as asking them to learn another programming language. So it's not a reasonable ask to go to a database engineer and be like, hey, could you redo all of that in Python or something? And they'd be like, no, because it's written in C. Like that'd be a silly thing to ask. So we really got to meet developers where they're at. Okay, so let's see. I didn't show the source maps. We do have source maps working in that user interface thing. I'll show them real quick. This is a little bit funky, but you basically have to, when you do the prove rs command, you have to tell it save the intermediate SMIR, and then you can do this view command and tell it and give it that intermediate SMIR information, and then it's a little more informed about how it displays the given proof. So I'll run this real quick. Oh, no, that's not what I wanted. There we go, okay. It's a little more informed about how it runs the given proof once you do that, because it has that smear.json file that it has the source maps and the spans and the function names and everything present in that. So I'll show you what that looks like. And maybe that's a convincing argument for why we should extend this format some more. We're running out of time. Okay. Sorry, I do know how to ramble. Yeah, so now we have like the function name, okay, I'm in compare less than, I'm in compare less than equal, and it gives the span information, like that's from CMP line 6, CMP line 28 or something like that, right? So just a little more information about orienting yourself where you are in the Rust program. That could obviously be turned back into something where it's pointing, it's actually in your VS Code interface and it links you to that part of VS Code. Okay, I wanted to finish with some learnings from Web3, having been doing commercial formal verification for a while. Scaling, got to do the modular thing, got to do the compositional symbolic execution, like the contract stuff that you guys were talking about. That was resonating a lot. Bounded model checking, it's not enough. Like loop unrolling, not enough. You have to be able to supply invariants. We have a way of doing that. We found several bugs that other tools that did bounded model checking missed. That is especially true when you're not just talking about generic properties like does list append work, but business logic specific functional correctness properties, it especially becomes true. Functional correctness and invariance, those cover the vast majority of properties that are actually needed. Liveness properties and stuff like that, almost never have we had to look at those. But that could be because we're in the smart contract domain, so keep that in mind. Annotations, DSLs, IDPs, no one's gonna use them. Like you have to meet the developers where they're at. And all the automated checkers that are useful and fast and providing immediate feedback should just be built into the compiler. That's kind of my opinion there. Okay, that's it. Yeah.
You mentioned there's a Python layer and a Haskell layer. I'm confused which one is responsible for what.
So the Haskell layer, which Yoast is the main author on actually, does symbolic reasoning, symbolic execution. So it's able to do like symbolic unification to decide which rules apply. It's able to do symbolic subsumption. Yeah. Yeah, that's kind of the symbolic interpreter basically, but it's actually broken into many different atomic operations that can be used to build a symbolic interpreter. Python just does the orchestration. It's like, because we have like the concrete backend, which is an LLVM code gen thing. We have the symbolic backend. We also generate a parser for languages that actually have a cool textual format, so you can just parse those directly. And so in Python, you can say, call the parser, get the program, load it into the symbolic, do a concrete, make a fuzz. Like the Python lets you do all that kind of from an API. So I'll just show you like an example of, this is like the main Python. So here we build the K-MIR object, which gets access to all of those tools I described, right? And then we build the smear for that Rust project, right? And then we parse that into K-MIR or something like that. And then we actually run using the LLVM backend, the concrete interpreter, and then we print that out or something, right? So it's just, and then here's like where we implement ProveRS. We build again the K-MIR object, which has access to all those tools. We call ProveRS, So Python is just kind of like this orchestration layer for plugging all these tools together because they all speak the same two languages, which is either cast or core, depending on the level the tool works at. So it's almost like an API access language or something. Yeah. So we haven't tried K-MIR on large-scale Rust code because it's not ready. We have tried Comet on real-world smart contracts for Sorbonne, and those are, those are on the scale of thousands of lines at most, right? So they're not large, I would say, and they're also very minimal in terms of the dependencies they pull in and stuff like that. And it works fine, but that's executing at the WebAssembly level, so it's a lot slower than executing at the MIR level will be. So.